Now let us look at another scenario where, in addition to the desired signal, there is another interferer present, but at a different frequency, and both the signals are passing through a nonlinear signal processing chain. This is our desired frequency. This is a strong interferer. Signal is passed through the nonlinearity. Let's say the nonlinearity is still third order. Then we expect that the V out is going to have this A naught plus A1. Then we have these two signals. So let's call this one as A1 cos omega 1t. This one is A2 going to be A1 cos omega 1t plus A2 cos omega 2t. Then we have the quadratic term A2 cos omega 1t plus A2 cos omega 2t whole square. Cubic term A3 A1 cos plus A2 cos t cube. We are ignoring the higher order terms. Here, if see, so as such, these two signals are at different frequency. So fundamental term, if you see, they are not the same frequency. So we can still distinguish the desired signal from the interferer. But as a result of these nonlinearities, it is possible that some part of this interferer may actually translate in frequency to the desired frequency of omega 1. So let's see that. So if you look at the second term, it is going to give rise to the frequencies which are at 2 omega 1 and DC, 2 omega 2 and DC, and then there will be a cross term which will give rise to frequencies at omega 1 plus minus omega 2. So all the terms coming out of this quadratic term will not be as such lying on top of the fundamental frequency of omega 1. Now let us look at the cubic term. This cubic term will anyway be giving us the third harmonic and the fundamental for omega 1 as well as omega 2. Okay, so that gain compression we are already aware is going to be present because of this cubic nonlinearity. In addition to that, we'll be also having this cross products. These cross products, there will be a term which may actually be having amplitude decided by the interferer, but the frequency will be at omega 1. So if we focus on those terms, so here I am ignoring the other part. So all the terms which are not exactly falling on top of omega 1, I am ignoring. So there will be no term at omega 1 due to the quadratic nonlinearity. And let's look at the cubic nonlinearity. So here we know we will be getting term which is A1 cube cos cube omega 1t. Then there is this A2 cube omega 2 cube. Then we'll be having 3 A1 square cos square omega 1 t a2 cos omega 2 t plus 3 a1 cos omega 1 t to a2 square cos square omega 2 t. From earlier derivation, we already know that this cubic term is going to give rise to term at the fundamental frequency of A1, omega 1. This term will not give any term at omega 1. Here also, if we see, so this cos square omega 1 will give rise to terms at DC, and 2 omega 1 multiplying with omega 2 will be giving frequencies at omega 2 and 2 omega 1 plus minus omega 2. So again, nothing at omega 1. Whereas, if you look at this term, here we are getting a DC component as well as 2 omega 2, and when it is multiplied with omega 1, we will be getting a term at omega 1 also. Okay, so ignoring all the terms which are not appearing at omega 1 and just writing down the components at omega 1, we see it is A1, which is the fundamental part. Then we are going to get, because of this cubic nonlinearity, we are going to get this A3 3 by 4 A square. Then, because of this cross product, we are going to get 3 by 2 A1, A2 term also involved. Okay, so this A2 square is multiplied with this with the other 3 by 2 A1 A3. And overall, it can cause huge desensitization of the gain. So now if A2 is pretty high, then we can see that compared to the gain at a small, means without interferer, so A1, now we are going to get a effective gain, which is, and if the A2 is pretty high and the system is nonlinear, then this term can dominate the gain, and most of the cases this is going to be with the A1 and A3 are going to be opposite polarity. So there will be huge reduction in the gain for the desired signal. Minus 4 EM square minus 3 by 2. This is the gain in the presence of strong interferer, and it results in gain desensitization. It is also called as blocker. If the blocker interferer is very strong, then there is no gain for the desired signal. So we have seen the case when you have only a single tone as the desired signal, and in the absence of blocker and the presence of blocker. Now let us take a case where instead of just a single tone, the desired signal itself contains two tones. And that is a very practical case, because in general, when there will be modulation, then this desired signal will not be just a single tone, but you can think of it as having as if a collection of multiple tones. Let's say we have these two as the frequency components which are within the band of interest at omega 1 and omega 2. This is the V in of t, a cos omega 1 t plus a cos omega 2 t. And now we are going to pass this signal through a nonlinear stage. Now we are assuming a nonlinearity till third order. We have a DC component, then a fundamental term. By now we are already familiar that this quadratic term is going to give rise to components at omega 2 omega 1, 2 omega 2, the DC terms, and omega 1 plus minus omega 2. So this omega 1 plus minus omega 2, if you want to see, let's see the outputs. So we have this amplified terms at the input frequency because of say term. Then there will be some DC term also. Now we are talking about terms at 2 omega 1 and 2 omega 2. Then the quadratic term will also give rise to omega 1 plus minus omega 2. So we are going to get, now let's look at the cubic term. So here we are going to get the third harmonics of omega 1 and omega 2 in addition to the some effect on the fundamental. There will be some components, these frequencies. In addition to that, as we have seen earlier, there is going to be this 2 omega 1 plus minus omega 2 and 2 omega 2 plus minus omega 1 kind of terms also. Those terms, if you look at 2 omega 1 plus minus omega 2, then 2 omega 1 is somewhere here, and omega 2 is somewhere here. So this difference is again very comparable to this omega 1, omega 2 frequencies. This 2 omega 1 minus omega 2, for example, we are going to get somewhere here. And if we see this difference, this delta omega, the difference delta omega is same as the spacing between the two tones we started with. Problem is, whatever filter we may be having to select the desired signals, these terms due to this cubic nonlinearity will also be passing through the same filter. If I only write frequencies which are close to the fundamental, so in band, these are going to be this linear terms. Already know these cubic terms. Then we have terms due to this cross product, which is going to be A3. If we say delta omega as omega 2 minus omega 1, you can see that this 2 omega 1 minus omega 2 is nothing but omega 1 minus delta omega. 2 omega 2 minus omega 1 is omega 2 plus delta omega. Both of these very close to omega 1 and omega 2 if delta omega is small. See the problem? This delta omega can be really small. We can now expect a lot of such terms to be present in the output spectrum. So these terms are also called as intermodulation terms because of the modulation of the terms which are in band, and specifically these are called as third order intermodulation term because these terms are the result of the third order nonlinearity. There is also one more term appears at the fundamental frequencies, as we see in the case of the gain desensitization. So that term will be 3 by 2 q omega t plus cos, and the intermodulation term is appearing at frequencies 2 omega 1 minus omega 2, 2 omega 2 minus omega 1. The coefficient of 3 by 4 A3 AQ. The relative IM3 captures the strength of intermodulation components with respect to the fundamental component, and relative IM3 is expressed in log scale as 20 log of the strength of the IM3 component, which is 3 by 4 A3 AQ, normalized to the fundamental strength, which is A1A and this is referred to as DBC to emphasize that we are comparing the intermod component with respect to the fundamental component. This is 2 log of 3 by 4 A3 by A1 is square. And good thing about two-tone test is it can give an idea about the nonlinearity which is present in the system in the form of this intermodulation components, even when the input signal which has been applied is not as strong as which are needed for doing the 1 dB compression test. But let's say we are trying to find out the relative IM3 component. This relative IM3 component, as we can already see, is also dependent on the strength of the input which has been applied. So many times we want to characterize the nonlinearity of the system, which is not dependent on the amount of input signal we are applying. So let us try to plot the fundamental component strength and the intermodulation component strength as a function of input amplitude. So we know that the fundamental component is equal to A1A, at least at lower power. So let me say it is almost equal to A1A. For small input amplitude, and the IM3 component is equal to 3 by 4 A3 AQ. So if I plot these fundamental and intermod component in the log scale, then you will find that this fundamental component will be increasing at a rate of 20 dB per decade. So in the log scale, it is going to have be a straight line with a slope of 1. So if I plot the fundamental, it will look like this. This is going to have slope of 1. Whereas if I plot the IM3 in the same graph, it is going to have a slope of 3 because you see this Q vector slope is equal to 3. So as we increase the input strength, we know the fundamental and IM3 are going to follow this kind of trend. But as the input amplitude becomes very strong, in reality, other nonlinearity terms also will come into picture. And we know that fundamental strength will also taper out. In addition to that, IM3 component strength will also taper out. This is the kind of typical trend we are going to see. So if we extrapolate these two plots, we can say that at some input signal strength, the fundamental component is going to become equal to the IM3 component. So it may not be a real scenario because in reality both of these powers are going to saturate, but this extrapolation will give us an idea about how linear a system may look like. So if the IM3 component is lower in a different system, then we will be seeing a plot like this. So even though IM3 may saturate, but we'll see that this extrapolated point where these two, the fundamental and IM3 are going to go intersect, that point will appear at a even further value of input strength. So this point where the two extrapolated plots intersect gives us an idea about the linearity of the system. This signal strength or power at which this extrapolated plots intersect is also called as input referred third order intercept point. So here I will hit IIP3. IIP3 means that A1 AIIP3 is equal to 3 by 4 A3 AIP3 Q. Implies AIP3 is equal to 4 by 3 A1 by A3 square. So just like the AP1 dB, here this AIP3 also gives an idea about the relative values of A1 and A3. If you remember, we had got a P1 dB as square root of 0.145 A1 by A3. So if we compare these two quantities, we'll see that this IIP3 with respect to a P1 dB is almost equal to 9.6 dB. Okay, so this IIP3 point is going to be almost 9.6 dB above the P1 dB. So in reality, we will never be able to make the fundamental and IM3 component to be equal, but this is just an extrapolated point to characterize the nonlinearity of the system. Okay, so now we have got a value which doesn't depend on the input strength, and it again gives a fundamental relationship between this first order and the third order coefficients. It is possible to find the IIP3 point just by doing a single measurement. So, for example, let's say some small input strength of A, we find out what is the fundamental strength and what is the IM3 strength, which also gives us the idea about the difference in the two components in the dB scale. Easily see that this AIIP3 is going to be equal to this input signal which we have applied plus the extra signal strength which is required to make this delta P 0. And if you see this delta P, which is the relative strength of fundamental with respect to the IM3, it is reducing with a slope of -2. Okay, so this guy is increasing with a slope of 1. IM3 is increasing with a slope of 3. So the gap is reducing with a slope of -2. So it means if we know this delta P, we can directly say that AIIP3 in dBm is equal to A in dBm plus this extra input distance which is needed to make this delta P 0, which is nothing but delta P in the dB divided by 2, also equal to A in dBm minus m by 2. So if we are doing everything in this log scale, it is easier to do this simple arithmetic to find out what is going to be the AIP3. So from a single test, we can find out the AIP3, which is different than the 1 dB compression test, where we need to keep on increasing the input power till we see that the large signal gain has reduced by 1 dB. So in that respect, again, this is a very convenient way to characterize the nonlinearity of the system. So we started this nonlinearity discussion by saying that on the higher side, the amount of input signal which can be received is going to be determined by the nonlinearity of the system. Now we have found multiple ways to characterize the nonlinearity of the system. Now let us find out what is the range of signal which a system or a signal chain can process satisfactorily. So we are interested in finding out the dynamic range, which is in the range of input signal which can be processed by a network or Okay, so when we talk about a dynamics range, we need to know also what is the minimum signal which we can process. So if you remember, we talked about the effect of noise, and we talked about sensitivity. So even when there is no signal which is present, for example, if A is very low, still at the output we are going to get something. Okay, and this undesired component is the noise. So I am showing here what is the minimum output power we are going to always receive even when signal is not applied. This is shown as the noise floor. If we start increasing the input strength, output strength increases, but at the same time, intermod component is increasing, and beyond a value of a small a, we see that this intermod component is becoming higher than the noise at the output. So in such a scenario, we can say that in this region, we are limited by the nonlinearity of the system, whereas for lower value of input signal, we are limited by the noise of the circuit. This side limited by noise. This side limited by nonlinearity. So it helps when we increase the input signals because our output is also increasing. But beyond some time, beyond a value of a input signal, it doesn't help us, as we can see that these undesired intermod components are going to come into picture, and effective signal with respect to the undesired components, that ratio is going to only reduce. The maximum signal to noise or distortion ratio which we can get is going to appear at this point. Maximum signal which we are able to process without causing intermodulation components to, or the nonlinear undesired nonlinear components to exceed the noise floor. Minimum which we can apply, we already know, is the sensitivity. Maximum which we can apply is the Amax here. This specific way of finding the dynamic range of the network is also called a spurious-free dynamic range. There can be another definitions of dynamic range where we may say that we can apply the input till the input amplitude or the input gain reduces by 1 dB, and the minimum is going to correspond to the sensitivity of the circuit. That is going to give you another definition of dynamic range. But we will see that most of the time we are limited by the nonlinearity whenever we are trying to design circuits for wireless systems. So in such a scenario, this definition of dynamic range is going to be more useful. So let us try to find out what is this Amax. Okay, and before that, let me define this dynamic range as spurious-free dynamic range, or SFDR. We can assume a 50 ohm system and convert all these amplitudes into power, and we can write this as P sense as the minimum signal which can be received, and let me call the power corresponding to Amax as the Pmax. So we need to first find out what is the value of this Pmax. To do that, we know Pmax corresponds to the P in at which IM3 becomes equal to the P noise floor. The input referred noise floor, we also know, is equal to minus 174 plus 10 log B, okay, because we are integrating the noise in a bandwidth of B, plus the noise which is added by the circuit itself. So let me call it PIM3. So this Pin can be found out using the IIP3 relation, which we knew that PIP3 is equal to P in plus P in minus PIM3 by 2. That implies P in to be equal to PIP3 plus PIM3 divided by 3. And Pmax corresponds to the input at which the power of IM3 is equal to the noise floor. So it will be equal to 2PIP3 plus minus 174 plus so at this input power, intermodulation will be equal to the noise floor. So now we can write SFDR in dB as Pmax minus the sensitivity. So this can be written as PIP3 P input referred noise divided by 3 minus sensitivity, which is the input referred noise, along with that the minimum SNR. So on top of the noise floor, the signal needs to maintain some SNR for satisfactory demodulation. So it means the SFDR relationship will become 2 by 3 PIP3 minus the input referred noise, which is the same expression we derived earlier. Okay, minus the SNR bin. So now we have got an idea about what is going to be the dynamic range in the presence of noise as well as the nonlinearity of a system.